The title is about E8 and Leech Latthce. And this is a very special and timely talk because recently the Fields Medal was announced a few days ago. And there are 4 recipients. And the first one on the top left is the James Maynard. He is working on number theory about prime gaps in prime number, something like the twin primes problem. The one on the right, on his right, is Jun He, a Korean mathematician, and he is working on combinatorics. He solves several open problems using ideas from algebraic geometry. And this one on the lower left is Hugo Dominic Cohn. He is working on probability and statistical physics. And also he solves some open problem. That's all of them solve some well-known problem. The one I want to discuss today is the last one, Maryna Viazovska. And so happened that I know something about her work. Of course, I only know the application part. The theory part is very difficult. So the citation from the International Mathematical Union is like this. So he is awarded the Fields Medal because of her proof that the E8 lattice provides the densest packing of identical spheres in 8 dimensions. And furthermore, she has contribution to relate extreme mode problems and interpolation problems in Fourier analysis. So that is why she received the Fields Medal. And that is the 8th dimension. So today we will see some mathematics and something in higher dimension, higher than 3 dimensions. And the outline will be 4 parts. The objective of this talk is not to give anything new to it. I want to just define the problem of sphere packing in general in arbitrary dimension, arbitrary but fixed dimension. And then this is the general part. The packing may not be regular, may not be periodic. A special type is called lattice packing, which is much easier. And it turns out that in dimension 8, the more periodic regular packing achieves the absolute maximum in density. That is called the E8 lattice. So this is a open problem for many years. It is believed to be the optimum, but nobody can give a precise proof until the work of Maryna Viazovska. And her work was immediately generalized or adapted to another dimension, 24, for Leech Latthce. It is also shown to be the best possible sphere packing, lattice or non-lattice. So that is the problem. So today we will mainly look at the constructive part. The upper bound is too difficult. We will have some concrete example and illustration of the problem. Okay, that is the outline. If you have any comment or question, please don't hesitate to type your comment in the chat room. It will be something you would like to clarify. So let's start with dimension 3. This is already difficult and a very well-known conjecture and problem for more than 300 years. That is called the Kepler conjecture. The Kepler conjecture, 1611, it says that the density, the best way to pack sphere, the density is obtained by face center cubic, the one that is usually employed in supermarket in packing orange or any three-dimensional ball is called the face center cubic. We all know that it is the best one, but the proof why it is the best takes very, very long time to achieve. The major breakthrough is in 1996, Tom Hales and Samuel Ferguson, right here, is they reduce the problem to checking thousands of configuration, and they need to do this by computer. So by paper and pen is not possible for this problem because there are too many configuration. So this has some controversy because it is done by computer. Mathematicians very often do not accept proof by computer because there may be bugs or problem in your program. So it takes 20 more years or 30 years to finally settle this by giving a formal proof. So what they did here is to formalize their proof that can be checked by computer. So this is the computer proof assistance. They use HOL, Light, and Isabel. So they write down their proof in a format that can be understood by computer. Yet there is some component of computer involved in this check, but the kernel, the one that we believe to be true, is very small, and that is like a compiler. They can recognize all the proof steps and check that they are all correct. So finally, in 2017, it is also done by Thomas Hales and their collaborator. They really wish to settle this Kepler conjecture without any doubt. So nowadays, I think all of us believe that this Kepler conjecture is fully proved. So that's already very difficult in 3 dimensions. But some miracle occur in 8 and 24 dimensions. We can prove that using paper and pen only. No need for any computer programming. So that is the background. And the purpose of today's talk is just to define the problem. We will only give one very simple proof for the constructive part, the lower bound. The upper bound will not be discussed. Okay, so now let's go to the general case. N-dimensional space, n may be larger than 3. We define the Euclidean distance in Rn. As usual, just extend the Euclidean distance from 2 terms to n terms. Then that is called the Euclidean distance in the general case. And once we have a distance, then we can define ball or sphere or ball. And in today's talk, sphere and ball will be regarded as the same thing. So in some mathematician or student in mathematics, sphere means the ball without the interior. So, but in today's context, ball and sphere will be referring to the same thing. We also include the interior when we talk about sphere. So BNCR, n is the dimension. This n is the dimension. C is the center. It's fixed center. It's a constant. It's just a point with n components, C1 to Cn. And the radius is denoted by R. And the ball or sphere center at C with radius R is just a set of points whose distance to the center C is no larger than R. And this D is defined as above, the usual Euclidean distance. So that's define the volume in the n-dimensional space. So everything should extend very naturally. Shear packing can be described by a discrete point. A packing can be uniquely or defined by just the center point. We just need to specify the center and the radius. The center will be denoted by P, P1, P2, P3. It is a infinite set, but countable, a countably infinite set. Let's denote it by some name, discrete point X. X is just a set of points in n-dimensional space. And we call this a packing if the ball center at this point has distance at least equal to 2r. Any 2 points that you can pick from this collection of points, the mutual distance between any pair must be larger than or equal to 2r, because we want to put a sphere of radius r center at each point. Then the resulting ball or sphere will be non-overlapping or just overlap just one point or touch at one point. They cannot have non-empty interior. So that is the meaning of sphere packing. Okay, so we just defining some terms in this slide. And next, we need to have some measure of the volume. What is the size of the n-dimensional ball or sphere? In n dimension, we still can calculate the ball by multiple integration. There are repeated n times, integrating the function 1. And the volume, or the set we integrate over is a n-dimensional ball with radius r. Here 0 doesn't matter, because we know that it do not depends on the center, only depends on r. So if we integrate that, it turns out we have a closed form formula in terms of the gamma function. That is pi to the power n over 2 times r to the power n divided by this constant. And of course, we know that it must depends on r. So it depends on r through the factor r to the power n. Pi is raised to the power n over 2. Okay, so this part is easy from calculus. And for example, when dimension is 2, dimension 2, this is pi r squared. Pi r squared is the area of the circle. The volume of three-dimensional ball or three-dimensional sphere is 4 pi over 3 times r to the power 3. And for 4 dimension is pi squared over 2. So here I just plot or list the constant. And let's draw a graph to illustrate some points. So let's plot dimension n in the horizontal axis. And here I will roughly plot the volume of a sphere with radius 1. So radius is 1. And if you look at this, then you can see that the volume will raise and then decrease. So somewhat counterintuitive. If you are first time looking at this table, the volume is not monotonically increasing, it is increasing up to dimension 5. So somewhere in dimension 5 is largest, then it will decrease to 0. And this is 8. We are interested in 8 and 24. So when the dimension is 24, the constant is quite small in compared to the others. So that is the shape of this constant. Okay, so that is the fact. There's no intuition or no explanation why 5 is the maximum. I don't have any explanation. It's just true by calculation. Okay, so that is the measure. Because we are talking about density, so this one is important in the problem formulation. Next, finally, we can define density. We will denote density by delta. So that is delta n. N stands for dimension. Given a set of points as the center of the packing, then we define the density by this quantity, taking lim sup of S approaching infinity. So what is S? S is the 2S is the side of a hypercube. So the picture on the right, you should imagine that as a n-dimensional hypercube. But here I only draw the case n equal to 2 on the plane. And we want all the sphere to be disjoint. So that is the key requirement. Or they may touch at one single point. They may overlap, but most overlap at one single point. And counting function. So for every hypercube with side to the power s, we count the number of center that lies inside this hypercube. The hypercube has volume 2s to the power n. So the volume is easy to calculate. And we count the number of points inside this hypercube, and mn represent this number. And this number multiplied by the volume of a ball with radius r. So that's roughly the volume occupied by the sphere, but maybe some of them is outside. So this tiny bit is lying outside the hypercube, but that doesn't matter because we are taking limit. Take limit as s approach infinity. And we are also taking lim sup, so guarantee that the limit exists. So that is always well defined for any x. And we want to have this density as large as possible by designing some pattern in the point set x. So that is the problem of sphere packing in general. There may be irregular spacing. So this is not periodic and maybe randomly looking. So in general, it could be a non-lattice arrangement, but still we can define the density by this quantity. Okay, so that is the starting point. But that's too difficult. And in most cases, it is much easier to describe the point set x by some very regular and periodic pattern, such as square packing or hexagonal packing. Then everybody understand what that is. When we say square packing, then you have this picture in your mind. And a sphere packing is called a lattice. If the center has some very good structure, we call that discrete abelian group in Rn. So that abelian group means it is closed under taking addition. So if x and y are 2 points as a center, then the sum is also a center. It's also closed under taking negation multiplied by -1. So any structure satisfying these two properties is called an abelian group, and they are discrete because they are discrete points in Rn, in the Euclidean space Rn. Okay, so that is usually how we specify and define a packing. Let's have some examples. So after all those abstract definition, let's see some concrete example, but in only dimension 1, 2, and 3. So dimension 1 is very boring. So this just one line, and this is R1. And everybody knows what to do. It's just some regular spacing. You may just regard it as C. The point set comes from integer. So integer already give the best packing in dimension 1, and the density is obviously equal to 1. So the case is closed. No more discussion. And the first interesting case happened in dimension 2. Dimension 2, we have hexagonal packing. So we know that the way you pack circle on a flat plane is using hexagon. Every circle should touch 6 other circles if you want to maximize the density. Okay, so the picture you have already seen that in the previous page. So assuming they are all circles with the same radius, then this pattern will give the highest density. And calculating the density is not difficult. So let's do that fairly quickly in order to give you some feeling about this problem. So just look at one triangle. So this is a pattern that can tile the whole plane. So for lattice packing, the computation of the density is easier than the general case. So in a equilateral triangle, we can occupy the 3 corners, and the one in the middle are empty space. So what is the density? So this one is occupied. The shaded area is 1/2 of the end of the circle. So let's suppose the radius is equal to 1. So without loss of generality, suppose the radius is 1. And the shaded area is exactly 1/2 of a circle. So that is pi/2 is the occupied area. Divided by the volume of triangle, and that will give the density volume of this triangle. And the triangle is also very easy to see because the side is 2. This is 60 degrees. And so this square root 3. Okay, so area is just square root 3. So the density is pi over 2 square root 3. And if you calculate that, you get 0.9069. So that is a very famous constant. The optimum packing by circle on the plane, you cannot get higher than 0.91 or 91%. And that is also easily done for construction. But how to prove that this is optimum, even for non-lattice packing, is not so easy. And take some time to prove that. Okay, so here we just do the constructive part. The upper bound, why you cannot improve upon this by non-lattice, non-regular pattern is something that requires proof. So, but today we will not go through any proof on the upper bound. The packing in 3 dimensions, let's also quickly review this, and everybody should know this. So as a warm up, let's also draw the pattern. So here the red circle is 3-dimensional ball. Imagine they are orange, so they are not circle, they are 3-dimensional object lying on your table. And suppose this center are denoted by, let's call them A, so the red one. So and we know that if you want to lay another layer of orange above this, then we can do, so there are several options to do this. And the first one, notice that this is green open space or deep hole in, let's call this point by B. So either you put another layer of orange on the location indicated in green color, or you may do the other way. In orange color is also fine. It will give another, let's call that C, give another arrangement or packing with the same density. So a packing can be done or can be described by this 3 special location. A is the ground level. And in the next one, we can pick either the blue one in green color or the orange one in the one in orange color. So something like this. A second layer, we put the sphere on position B. Third layer, we put on position C, and then repeat ABC, etc. Then we will get the face center cubic packing. You may also have AB. Then the packing is not the same. The geometry are different, but the density is the same. So one of the difficulty in dimension 3 is that the highest density is achieved by infinitely many patterns, as long as you do not have 2 consecutive lattice. So any two consecutive lattice should not be the same. So as long as you obey this rule, then the resulting packing is optimum in the sense of density. But they may not be periodic, may not be even lattice packing. So packing in dimension 3 looks like this. And if we calculate the density, you will get pi over square root of 18. So that is some standard exercise. Today you can find this in the internet easily. So our focus today is on dimension 8. So let's move on to dimension 8. Okay, so after the review of dimension 1, 2, 3, in dimension 8 and 24, something very special occur. And this happened in year 2016. In 2016, not so long ago. So in compared to the Kepler conjecture, so you see this is very recent result. The half-life of this type of this problem is very long. And this is based on some earlier work on Harvey Cohn and Noam Elkis. And so these two people already set up a formulation, some method to compute to obtain upper bound on the density. But they need some magic function to work. And this magic function is finally derived by Viazovska. And this just show that the E8 lattice in dimension 8 has density exactly equal to the upper bound. So this even for non-lattice sphere packing. So the difficult part is for non-lattice. As a lattice, then we know that E8 is the best lattice packing previously, but even for non-lattice case is optimum. This part is the real difficult part, and this is done by Viazovska in 2016, and the proof is quite short in compared to the Kepler conjecture. Is maybe 10 or 8 pages. Finding this magical function is very difficult, but once you have found them, verification is quite fast and easy. So this is some search problem, search for some very special function to plug into some linear programming bound. And the search involves modular form, which is very interesting, but we will not talk about. We are not able to talk about them today. And very shortly after, maybe 2 weeks or 3 weeks after the announcement of the work by Viazovska, they extended proof to dimension 24 to Leech Latthce. So basically the same principle, but they can find another set of magical function to prove that the Leech Latthce in dimension 24 has density just exactly equal to the upper bound. Therefore, it must be the densest possible sphere packing, even among the non-lattice packing. Because that is the achievement they obtain. So that is a summary of the packing in low dimension. So here I list dimension 2, 3, 4, 5, 8, and 24. So as the dimension 2 and 3 are called A2 and A3. A2 and A3, they have density 0.9069 and 0.705 respectively. And the history goes back all the way to Lagrange and Gauss. They show that it's the optimum among all the lattice. But to show that it's optimum among all the non-lattice packing require much more effort. And it was finally done by Hales in 1996. So that is the Kepler conjecture. In dimension 4 and 5, the lattice is usually denoted by D4 and D5. And they are just studied by Cohn and Solotorov in Russian. And dimension 8 is called E8. So we see that the best density that we can obtain is 0.2537. As a lattice, it is studied by Bridgefield in 1945. But the reason why it is the best among all possible non-lattice packing is only possible a few years ago, 2016 or 17. 17 is the publication of the formal paper. Okay, so that is the landscape. One picture that summarizes all dimensions. So in the horizontal axis, I plot the dimension from 0 to 45. So that is dimension. And horizontal vertical axis is density. And you can see some very special point right here. This occur in dimension 24. The solid blue line is the largest known density at that time. And so because this plot is done before the work of the Viazovska, and the upper bound by Beachfield is fairly close. So notice the very small gap at the point 24, at dimension 24. There's another point right here. This is dimension 8. So something very special occur in these two dimensions. After that, nothing like this occur above 24. So there is some special property of 8 and 24, so magical that we can find some very dense pattern in these two dimensions. Let's do one very easy lower bound on density. So this is a non-constructive pattern, and you can use this non-constructive proof to show that the density is at least 2 to the power minus n. This is true for every n, and because the proof is quite easy, I would like to go through this in this talk in order to give you some flavor of this type of problem. So what we want to show is that lambda n, there exists some packing x, so that the density is larger than 2 to the power minus n. So at least you get something no worse than 2 to the power minus n. And the idea is using some greedy approach or greedy algorithm, something similar to the greedy algorithm in computer science, in programming. And so the idea is to first generate some pattern randomly, no particular structure. So this is certainly not a lattice. So that suppose R is fixed. So let's fix R to be 1 without loss of generality, and so that every point has distance at least equal to 2. So the distance between any two is no less than 2. But this may not be good enough because we are generating randomly. So these are the points. It may occur that there is some empty space. If whenever you see an empty space where you can fit an extra ball in n dimension, then you go ahead and do that. And we repeat this until you can never insert any additional ball in this pattern. So that's why we call this greedy algorithm. And the resulting pattern certainly has no structure. And of course, we cannot claim that it is the best one, but at least it gives us some lower bound, some construction, which is not too bad. Okay, so suppose this is already saturated. So another term to describe this is saturated packing. Saturated packing, as you may guess, is just a packing that you can not insert any other ball in the empty space. This can be done by greedy algorithm. And once you can get that, then the idea is to suppose we increase the radius from 1 to 2. So now we consider this radius, which is now exactly equal to 2. Then there is certainly lots of overlapping balls. Then the new ball has to occupy the whole space R to power n. So this new ball of the original center, but now radius 2. The union of them must equal to alpha n. Because this is saturated, we can prove this by contradiction. If this is not equal, if this is strictly a proper subset of alpha n, then it will contradict the assumption that it is saturated. So we suppose suppose we have some point which does not belongs to. So suppose this point, a new point, let's call this P prime, that does not belong to any union, any ball with radius 2, summing over I. Then we can put an extra ball at this point P prime with radius 1, and that will violate our assumption that it is already saturated. Therefore, by this very simple observation, we must have 2 to the power n times delta, which is the volume of the enlarged ball with radius 2. The original, this must be larger than 1. So the original density is delta. Delta is the one. Delta is the density. Density when R is equal to 1. But now we suddenly increase R from 1 to 2. So that increase that ratio by at least 2 to the power n. Because we cover the whole space, 2 to the power n times delta must be larger than or equal to 1. So that means this density must be at least 2 to the power minus n. Okay, that gives a very loose upper bound, but very surprisingly, the best lower bound that we can obtain has the same order. Given all the effort of very clever person, we cannot improve upon the order. And this is roughly, I give 2 examples for lower bound density. Minkowski and Hawker, and they improved this by multiplied by this factor roughly by zeta n. Zeta is the Riemann zeta function, which is a constant. So the order doesn't increase. This is using some averaging argument. And also quite recently, 2013, Venkatesh, he finally have some asymptotic improvement with order larger than 1 over 2 to the power n. It improved by a factor of log n times n, but not for all dimension. For some sequence of dimension, some sequence, not all. It's already extremely complicated. So this problem is highly difficult. So that is some recent result on lower bound in density. So finally, let's move to dimension 8. I will describe 2 constructions for E8. The first one is in this page, and this is a union of two sets. So this one is easier to pass. So x1 to x8, 8th dimension. Each of them is an integer. x1 to x8, they are all integer. But we want the sum to be even. Sum of x1 to x8 is 0 mod 2. So we take this as its first part. And then we translate this part by 0.5, 0.5, 0.5. So there are 8, 0.5 here. So just move this in the direction of 1, 1, 1, 1, 1. But we add exactly 0.5 to each component. We also want x1 to x8 to be integer. And also they must sum to an even number, even integer. So we take the union of these 2 parts, then we get an E8 lattice. And for example, we may have 2, 0, 0, 0, 0, 0, 0, 0. This this belongs to the first set. We may also have 1 minus 1 0 0 0 0 0 0. This is also one of the lattice vector belonging to the first set. For the second one, we may just add a 0.5, 2.5, 1 half, 1 half, 1 half, 1 half, 1 half, 1 half, and 1 half. This is another lattice vector. Okay, so this construction is very explicit, and let's do some exploration. So let me ask the question of counting the number of vector that is closest to the origin. This is called the kissing number. And let's show that this is another magical number, 240. We can count that there are exactly 240 other spheres that touch the sphere center at the origin. So this is also called the find the shortest vector in the lattice. 240, and there are two classes, 3, 4, 5, 6, 7, 8. So to achieve the norm of 2, something like this, the norm is equal to 1 plus 1 square root. Norm is square root 2. So we can pick any two components, insert a plus or minus 1 in each of the chosen components. Then this gives rise to 8 choose 2 times 4, which is 102 vector of this type. We may also have some plus or minus 1 half from the first to the last component. This also gives a vector of norm square root 2. And we can choose the sign in any even, that must be even number of plus and even number of minus. So they are totally 2 to the power 8 divided by 2. We divide by 2 because the number of plus sign must be even. So that gives rise to 128. So totally we add them, we get 240. So that is called the kissing number of E8 lattice. A sphere in this lattice will touch exactly 240 other spheres in the neighborhood. And we can show that the density is pi to the power 4 divided by 384. And because of time, I will not go through this derivation. Another description is the generator matrix. This is more linear algebra, and every row represents a lattice vector. So we have to look at this in every row. 2 0 0 0 0 is one of them, as we have seen as we saw in our last slide. 1 minus 1 and all 0 is another one. We can also have all the components equal to 1 half. And this, we can take any integral combination of the H row in this matrix. So this is called the generator matrix because it is like a basis of the lattice, but the coefficient must belong to integral combination. That is called. That's another very handy description of the E8 lattice. So it is very concrete and explicit. Just take this matrix and multiply by integer vector, then you get the whole E8 lattice. Right, and I would also want to highlight some connection to coding theory. And so Hamming code is some very basic. This is 7-4 Hamming code. dimension is 4 and length is 7. So here 1 and 0 are binary number. We have 1 plus 1 equal to 0 in this calculation. And we all know that it can correct an error. There are 16 code words in total, and what you are looking at this slide is the 16 code word. This is the length 7. To obtain E8 from Hamming code, first extend this to length 8 by parity. So H4 extended Hamming code by appending a parity check bit at the end. So this one is the parity check bit, so that in every code word, the number of 1 is equal to an even number. So every code word, you check that either have 4-1 or H1 or 0-1. The weight distribution is very uniform. So these all have weight 4, exactly 4-1 in each vector. This is weight 0 and weight 8. So the minimum distance is equal to 4. Okay, so using this H4 extended Hamming code, we can have another construction of E8 lattice. So we define this by taking all the integer vector in H dimension, such that if we reduce modulo 2, every component we reduce modulo 2. If the result is one of the vector in the extended Hamming code, then we say that this vector is a lattice vector in E8. So for example, maybe 2 minus 2, 0 to 4, 0 to 0. This is an integer vector. We reduce mod 2, we get all 0. This is the first code word. So therefore, this one is a vector in the E8. So this is a very simple criterion to define a set of points. And this will give another description of the E8 lattice in terms of Hamming code. So there is a very intimate connection between serial packing and coding theory. In fact, given any linear code, there is a systematic method to construct a lattice packing. And 240 is this magic number. And we project this to 2-dimensional space, then we get this pattern. This is quite famous, and this picture is taken from a home page in John Byers. So there are lots of mathematical connection to other areas, such as Lie algebra. E actually stands for exceptional Lie algebra in dimension 8. But of course, we are not going in that direction today. And finally, let's quickly talk about the Leech Latthce. And similar to the E8, we can also construct this using a binary code. And in this case, we use another famous code called the binary Golay code of length 23. This is very famous because it is one of the perfect code for binary alphabet. It has length 23 and distance 7. As a cyclic code, we can generate this code using this particular polynomial. So construction is, there are more than 10 construction for the Golay code. And there are lots of structure in this code also. And for our purpose, we first extend that to length 24, just adding a parity check bit at the end, and hence increasing the distance from 7 to 8. Because there are too many code words, I'm not able to list all of them here. And the recipe, the method is to take any vector in Z24, or each component is an integer. And suppose each of them reduced mod 2 is some number, m. So here m must be either 0 or 1. There are two cases, either 1 or 0 for the number m. M is 0 means all of them are even. M is 1 means all of them are odd. And You also need to check the sum of the component xi is 4m mod 8. And this m is certainly the same as this m. The last criterion is that xi minus m divided by 2 reduced mod 2 is exactly a code in the Golay code, in the extended Golay code of length 24. And every integer vector satisfying these 3, 1, 2, 3 criterion is defined as a vector in the Leech lattice. It is first discovered by John Leech in 1967. And it has a lot of amazing property. And I list some of them in this slide. The first one is, of course, is density. Density is pi to the power 12 divided by 12 factorial. And now we know that it is the highest, the largest density, even among all the non-lattice patterns. This is done by the group of authors in 2016. And the kissing number is this number. It's very large, 195650. 19506, more than 19500 neighboring sphere for each sphere. So it's very extraordinary. And another very remarkable fact is that the automorphism group is very large. And it is shown by Conway in 1968, just 1 year after the discovery. So after this discovery, J.H. Conway spent a lot of effort to derive the automorphism group, and he showed that the order is this very huge number. And he also understands the structure of this automorphism group. And automorphism group is just a subgroup in the orthogonal group. O24 are the group of all orthogonal matrix, all 24 by 24 orthogonal matrix that preserve the lattice point. And he showed that there are these many 24 by 24 matrix that preserve the lattice points. And among this group, if we mod out by the center, then we give a simple sporadic group of this order. So this is a very remarkable discovery of J.H. Conway, and he is famous for this discovery. So we can imagine at those times there's no computer. At least Conway I definitely know that he are not using any computer in this computation. And final remark on simple group. So simple group is the building blocks of all the finite group. And there is a very long effort for the whole community of mathematicians to find and classify all these simple finite group. It takes more than several thousand pages of paper to finish the proof, one of the longest proof in the history of mankind. And finally, this is solved at the end of the last century. And there are 3 general types. The first one is cyclic group of prime order, alternating group, and groups of Lie type, plus 26 sporadic simple group, which does not belong to the above 3 types. And among these 26, 3 of them are derived from the Leech lattice. So from the Leech lattice, we can find 3 different simple group, and this is why it is very famous. The Leech lattice is very famous within the mathematics community. Yes, that is our final comment. All of them are mathematics, and for me then, or for us, we want to do something new or apply the lattice. And in fact, E8 lattice is in the standard of speech coding 729.1. It is in the standard because it's extremely good performance, and efficient encoding decoding is also available in hardware. So it's very fast and applicable. It also has application in other areas such as storage, wireless, communication, and data hiding. So solving the math problem is extremely hard, maybe impossible for ordinary people like me, but applying them is something that we can do. There are lots of other applications. The one I want to mention is the cryptography. We have some post-quantum cryptographic scheme that is based on lattice. So they are very useful in constructing cryptographic scheme. Yeah, this is the reference. You may, if you want to learn more, I would recommend you to read this book, Lattice Coding for Signals and Network. This is written for engineering, not for mathematician. You can also take a look at the last book, Lattice Applied to Coding and Reliable and Secure Communication. So this two book is something that's readable. If you are more mathematically inclined, you may read this new, very recent paper by Viazovska and her friend. It is about energy minimization in the E8 and Leech lattice. So they show that these two lattices is also optimum for energy minimization. This has application in physics. Yes, that is the end of what I want to share today. Exactly one hour. Any question or comment? And if no, then we will stop the recording at this point.